Okay. We can approximately, we can assume fringing fields are not important. You can solve for all the electromagnetic modes inside this parallel plate. And that you have learned in your undergraduate course, parallel plate waveguide. What kind of modes does it have? Okay? And so all the modes are given by this kind of resonance frequency approximately. N pi over L squared, N pi over L squared, L in the 2 dimensions, assuming that the fringing field effect is ignored, okay, that the current goes to 0 abruptly at the junction, we don't worry about field leakage, and then that in the 3rd dimension, the number of modes is p pi over d squared. Does this formula look familiar to everybody? Resonant modes of a cavity. Okay. And then we want to sum over all the 0-point energy as a function of d. And so what we need to do then is to sum over m and p, all the possible modes. And then there's a prime here that denotes something that we have all the 0-point energy of the system. Okay. The prime means that there's one particular mode that has no pair. If you look at the parallel plate modes of a waveguide, for every TE mode there's a TM mode. Okay, for every TE mode there's a TM mode. And they have the same resonance frequency. Except for one, which is the TM mode. There's one that where the electric field goes like this. The electric field goes like this between the parallel plate. This is plus minus n. So for this mode, the E field looks something like this. There's no corresponding mode that is the pair of this mode where the H field looks like this. Okay, no such mode. So this prime means that everything is paired and should be multiplied by 2 when we do the mode counting, except for this TEM mode, which has no pair. And we should pick out the 2 factor. That's what the prime is. Is this understood? Remember the parallel plate waveguide, there's a TEM mode, and that mode has no cousin. Okay, it doesn't have a cousin brother. But all the TE and TM modes between the parallel plate waveguide would have the cousin. TE mode has the cousin as TM. Is that clear to everybody? Okay, if it's clear, then I don't have to explain why this prime is there. Okay? So, when we sum this, then it will be coming H bar C. Okay, I can plug in this omega from above, you get H bar C. And then M and P, the prime indicates that for the TM mode, I don't double it. Or I should divide by half. Pi over d squared. Okay, so I just sum over. Actually just a plain substitution. And then I'm going to sum over the m's and the n's. The m's and the n's are in the actually x and the y direction. If I were to call this x, so this should be x. This should be y, right? This should be z. So the m's and the n's are sum over the y direction. So we can actually, in the limit when L goes to infinity, m pi or pi over L becomes delta kx, and then pi over L becomes delta ky. Okay, then m pi over L is equal to m delta kx becomes kx, and then this would become n delta ky becomes ky. So I can actually convert this summation into integrals. There will be a p prime integral map, or summation map. Okay, then the summing over m and n can be converted into an integral. Okay, so I need to put in delta kx, delta ky here, and then divide by 1 over delta kx, delta ky over here, which is actually according to this formula, L over pi squared. So I need to put in an L over pi squared on the outside, and then leaving this on the inside and convert the summation inside into an integral. And the p summation is still over infinite region, okay? Except that I don't double I should multiply half of the first mode, and then the rest becomes integration. 0 to infinity dkx, 0 to infinity dky, kx squared plus ky squared. This one becomes kx, ky squared plus d pi over d squared. Okay, so this is equal to that. And then my next task is actually to sum this. To show that it has a closed form summation. And second is that if I do change the separation a little bit, I can find the force exerted on this thing. But unfortunately, these integrals don't converge. They don't converge, they diverge. They are all divergent integrals. Okay, they are all divergent integrals. And so in order to make this thing converge, what we should do is actually to first assume that the separation between the two plates is infinitely long. Let d goes to infinity and compute this summation. And then subtract the energy of the finite plate. Okay, we take these two and then subtract them. And then hoping that the infinities will cancel each other. We are only interested in the difference. So this is called renormalization method. You encounter this in quantum electrodynamics and quantum electromagnetics. Quite a bit, divergent summation and divergent integral. They don't have meanings. So we subtract two of them to get a finite result. So the first thing we should do is to actually find out what this thing is when the separation is infinite. And if you do that, then this other thing also becomes an integral. So you actually would have three integrals. And then you convert this thing into an integral as well. So you will put a d over pi in addition on the outside. And then you will have dkx, dky, dkz. All three of them. Okay? And then you have this thing over here, which is kx squared plus ky squared plus kz squared. And you notice that all these things are not converging, because if you just take one of them, for instance, when kx or kz goes to infinity, this integrand goes as kz. Okay? It goes as kz and you cannot sum this thing. So the only rationale to this kind of thing is to do differences. That's how people get around this anyhow. Okay? But I think of it differently. I think that we shouldn't never take these summations to infinity. Because when you take give summations to infinity, what it means is that wavelengths can become infinitely small. Wave numbers can become infinitely large. Okay? That means that you can deal with modes whose wavelengths are extremely short. I don't think nature allows that. Space is not infinitely divisible. Just like you cannot break space into tiny bits and tiny bits and tiny bits forever. But continuum mathematics allows us to do that. Okay? Allows us to work with wave numbers that are infinitely large. But what we should do is that there should be an upper limit as to how small you can measure length scale. And that this thing should be truncated in the upper limit anyhow. Okay, you will find that if I were to truncate this integral with an upper limit, the final answer when I take the difference does not depend on that upper limit. Okay? We should think of this as conveniences of mathematics, but it's not a true reflection of the real physical world. Okay? So we come back after the coffee break and finish up on how to take the difference of these two. Okay? So maybe you want to hand out your forms now.